Hello everyone. My name is Yi Lin, and this is my partner Lucas, and we are both in our fourth year of environmental engineering at the University of Alberta. Drawing inspiration from our courses and our passion for renewable energy, we will be presenting a holistic cost-benefit analysis of renewable energy options in Alberta as our integrated project. Here is a quick outline of our presentation. To understand the need for renewable energy, we first need to understand the history and current state of the energy industry. Alberta's history in oil and gas began in 1914, when the first major oil field was discovered in Turner Valley. On February 13, 1947, a major crude oil discovery, Leduc No. 1, was found. This striking discovery began Alberta's oil boom. Currently, Alberta is the largest producer of crude oil in Canada, accounting for over 84% of total Canadian production in 2023, producing 4.3 million barrels a day, with 3/4 of it coming from the oil sands. This crude oil is exported to other markets across the country and internationally. The rest is refined into transportation fuels and other oil products to generate heat and electricity for buildings and to manufacture products. There are many environmental impacts and concerns from oil and gas, such as air pollution. Methane is a potent greenhouse gas with a global warming potential more than 25 times that of carbon dioxide. Volatile organic compounds are also produced, which is a group of chemicals that contribute to the formation of ground-level ozone or smog. Ozone can cause a wide range of health effects, including aggravated asthma, increased emergency room and hospital admissions, and premature death. Chemicals from oil and gas production also contaminate the soil with pollutants like heavy metals and radioactive material, which prevent the growth of vegetation and the habitat for wildlife. Due to surface runoff, the chemicals can make their way onto agricultural land and contaminate the food we eat as well. If these contaminants are not remediated, they can travel into groundwater through seepage and contaminate our aquifers. Water contamination degrades our water quality and causes illnesses and deaths, while also being harmful for aquatic life and our ecosystem. As a major player in the oil and gas industry, Alberta is facing the pressing need to transition from its traditional reliance on fossil fuels to renewable energy, as there is a global shift towards sustainability. According to the Government of Canada, renewable energy is energy derived from natural processes that are replenished at a rate that is equal to or faster than the rate at which they are consumed. Some benefits of renewable energy include: it emits little to no greenhouse gases and air pollutants, offering significant health benefits. It has lower and steadier prices, which keeps energy affordable and reliable. It fosters economic development, creates jobs, and helps tackle gender inequality, benefiting local communities. It requires lower use of water and land. It decentralizes and democratizes how energy is produced and consumed. It supports climate change mitigation, adaptation, and resilience. Due to Canada's large landmass and diverse geography, we have many renewable energy sources such as moving, water, wind, biomass, solar, geothermal, and solar energy. However, onshore wind and solar energy photovoltaic are the fastest growing sources of electricity in Canada and generate zero carbon emissions, and as such will be the two renewable energy sources analyzed in our project. Wind energy is a form of renewable energy that uses wind turbines to convert the kinetic energy of the wind into electricity. The amount of kinetic energy converted into electricity depends on air density, rotary area, wind speed, and wind direction. One major challenge with wind energy is its reliability, as wind speed varies both spatially and temporally, generating fluctuations in energy output. Thus, in order to integrate wind turbines into the electric grid, models, simulations, and estimates for future wind speed conditions are needed. Solar energy is a form of renewable energy that converts energy from the sun into thermal or electrical energy, and is currently the fastest growing source of power. Three main types of solar energy are photovoltaics, solar heating and cooling, and concentrated solar power. Solar energy shares the same challenge as wind power with resource variability, as it requires ample amounts of sunlight, as well as battery storage for excess energy generated. One benefit of solar energy in comparison to wind energy is it is more space efficient and can be integrated into commercial or residential areas. The Renewable Electricity Act is legislation that demonstrates Alberta's commitment to increase the generation of renewable electricity to ensure that by the end of 2030 at least 3% of electricity will be produced by renewable energy resources. This transition to renewable wind and solar power offers a cleaner, more sustainable alternative to fossil fuels and contributes to global efforts to reduce greenhouse gas emissions and combat climate change. Furthermore, increasing renewable energy projects will create new jobs, improve public health, and offer more economic diversification and energy security for Alberta. This is a strategic move for a more sustainable and prosperous future as it positions Alberta to remain a leading energy producer in a rapidly evolving market. As defined by the Brundtland Commission, sustainability is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Sustainability is a comprehensive approach to lasting prosperity, which recognizes that environmental, economic, and social dimensions must all be considered. These dimensions are the three pillars of sustainability. Environmental sustainability refers to all Earth's natural systems being kept in balance, and the natural resources within these systems are not used up at a rate faster than they can be replenished. Economic sustainability takes into account that economic systems and resources are intact and widely available to secure the livelihood of all communities. Social sustainability indicates the importance of universal human rights and basic necessities being attainable by all people without discrimination, who also have access to enough resources to provide an environment for a healthy and secure community to exist and flourish. Our project will engage with all three pillars of sustainability through a holistic analysis of each energy source. This brings us to our research question. What is the best renewable energy option for Alberta in the future? What can potentially replace or supplement the oil and gas industry? Next, we will discuss the methodology of our project. The scope of our study will include both renewable energy systems, utility-scale solar photovoltaic and onshore wind, and conventional fossil fuel systems. Smaller-scale residential and commercial solar will be considered for applicable variables. The fossil fuel generation considered will be natural gas, as it comprised 63% of Alberta's total electricity generation in 2021, and crude oil. Crude oil is used as an energy fuel source, not electricity generation, so any quantitative measures for electricity will not be applicable. Coal will not be considered due to the coal generation phase out in Alberta in June 2024. The steps for the research process are as follows. First, we will select the variables for our cost-benefit analysis. The requirements and assumptions for the variables were defined, leading to the determination of the variables. Both qualitative and quantitative data collection approaches were applied to ensure a holistic understanding of the various factors. The factors were chosen due to applicability and prevalence in related studies. Next, we will complete data collection for each of the variables and energy sources. In this step, the qualitative and quantitative data was collected through desk research based on published government, academic, and organizational publications. The last step of our methodology is analysis, where we will use the data collected to examine the economic, environmental, and social aspects of each type of energy generation. Here are the results of our study. The first variable chosen is the levelized cost of electricity, which is used to estimate the cost of electricity produced over the lifetime of a generating plant. Its value equals any revenue generated per unit of electricity that would be required to recover the costs of building and operating such a plant. This variable is useful for comparing different electricity generating technologies as it accounts for unequal lifespans, capital investment, and operation and maintenance costs. As seen from the table, the range and average levelized cost of electricity values for onshore wind, utility-scale solar photovoltaic, gas peaking, and gas combined cycle was found. The data found onshore wind to have the lowest cost at $50 per megawatt hour, with solar photovoltaic and gas combined cycle in similar ranges. Gas peaking was found to be higher at an average of $168 per megawatt hour, meaning there are significantly more costs in the plant lifetime in comparison to its electricity produced. Levelized cost of electricity is not applicable to crude oil as it is an energy fuel source and does not generate electricity. The next variable chosen was payback period, which is a measure of how quickly cash flows are generated to cover the initial investment. As seen from the table, onshore wind, solar photovoltaic, natural gas combined cycle, and crude oil facilities all have similar payback periods, with tight oil being notably lower at 2 years.
Energy return on investment was the next variable chosen, which is the ratio of the usable energy delivered during a system's lifetime to the invested energy required. For electricity generation, both wind and solar had similar energy returns, with natural gas being significantly lower, whereas for thermal energy, natural gas had a fairly high energy return compared to oil. A higher energy return on investment is more desirable as it represents a larger portion of energy generated to energy invested in the system. Thus, a natural gas plant is the most desirable for thermal energy, with wind and solar energy being more desirable for electricity generation. The next variable chosen was energy payback period, which is a measure of the time it takes for the plant's life cycle energy requirement to equal the energy it has produced. The energy payback period for renewable energy was found to be 5 to 8 months, and half a year to 2 years for wind and solar energy, respectively. Direct values for energy payback periods for natural gas or crude oil plants were not found in literature, so the values were calculated using the known energy return and average plant lifespans of 30 years for both sources. For natural gas combined cycle and oil plants, energy payback periods range from 2 to 15 years. Renewable energy sources were found to have a significantly faster energy payback period compared to fossil fuels. Employment opportunities was the next variable chosen. In 2022, clean energy and technology companies employed approximately 101,000 people in Canada, with 16% operating in Alberta. In 2023, oil and gas accounted for 181,000 direct jobs and 265,000 indirect jobs in Canada, with a large portion in Alberta. Jobs in the clean energy sector are projected to grow by 10% yearly, adding around 419,000 clean energy jobs to Alberta by 2050. Additionally, many jobs in the clean energy industry require transferable skills from works in the oil and gas industry. The next variable chosen was efficiency, which varies for different fuel sources, but in general is a percentage of the energy that can be converted into electricity. Wind, simple cycle natural gas, and oil all have similar efficiencies. Solar comes in a bit lower, but is expected to improve as the technology continues to develop. Natural gas combined cycle has the highest efficiency as the combined cycle reduces thermal energy losses. For a more environmentally focused variable, emissions were chosen, which is calculated in grams of carbon dioxide equivalent per kilowatt hour. Measuring carbon dioxide equivalent takes into account the various types of greenhouse gases emitted by each source, as natural gas and oil also emit methane and nitrous oxide in addition to carbon dioxide. Renewable energy sources emit significantly less greenhouse gas emissions than fossil fuels, making them more environmentally sustainable. Onshore wind was found to emit the least amount of greenhouse gas emissions. The next variable chosen was land use, which is based on the life cycle assessment and measured in square meters per megawatt hour generated. The average land use of ground-mounted solar photovoltaic is 19 and 12.6 square meters per megawatt hour for silicon and cadmium panels, respectively. This number drops significantly for solar photovoltaic installed on roofs. Onshore wind turbines have an average land use of 0.4, considering only the construction, but a full project area impact of 99. Natural gas plants have an average land use of 1.3. Land use comparison was not applicable for oil. Both utility-scale solar photovoltaic and onshore wind require a significant more amount of land to produce electricity compared to natural gas. Despite renewables' large land use requirements, some projects in Alberta are currently adopting dual land use for agricultural or livestock purposes, which is not possible for fossil fuel projects. These dual land use projects allow for community energy practices, fostering sustainable development. The next variable chosen was biophysical environment impacts measured qualitatively. Biophysical impacts of onshore wind and utility-scale solar photovoltaic include terrain, hydrology, vegetation, and wildlife. Common impacts for terrain and hydrology include increased erosion and sedimentation, changes to natural drainage, and soil and water contamination due to spills. Common impacts for vegetation and wildlife include habitat fragmentation, reduced biodiversity, and for wind specifically, increased mortality of birds and bats from turbine collisions. There are various methods to mitigate, avoid, and remediate these impacts, such as assessing the site to avoid proximity to delicate resources such as endangered species, prime farmlands, and wetlands, and to ensure suitability of the subsurface soil and groundwater conditions. Construction and land disturbance required for natural gas and oil can harm local ecosystems through erosion, fragmentation of wildlife habitat and migration patterns, and contamination of soils, groundwater, and surface water due to spills and leaks. Moreover, oil exploration and production induces secondary activities such as road construction and population settlements, further generating changes in the land cover and affecting the natural ecosystems. The next variable chosen was noise pollution, which is a type of unwanted sound produced at sound levels 50 to 85 decibels. Long-term noise exposure is associated with human health issues such as hearing loss, high blood pressure, and abnormal mental health. Noise has also been shown to have physiological and reproductive effects on wildlife, leading to their temporary or permanent displacement. One of the most common complaints of residents living near oil and gas operations is noise from activities such as traffic, well pumps and compressors, drilling, and flaring. The expansion of oil and gas infrastructure has meant that operations that produce large quantities of noise may be operating for extended periods of time. Various regulatory bodies have guidelines in place for noise allowed in residential, commercial, and industrial areas to reduce negative impacts. However, several studies have found that oil and gas operations frequently exceed those standards. Noise pollution from wind turbines depends on the atmospheric conditions, site topography, and the type of blade selected for the turbine. On average, utility-scale onshore wind turbines produce noise of 35 to 45 decibels when heard from 300 meters away, which is the minimum distance they must be located from a residential area. However, noise from wind turbines does not directly impact physical human health, although they still can be a source of irritation for residents nearby. Research into reducing noise from wind turbine design is ongoing, and there are other mitigation measures that can be implemented for project sites. Noise pollution is not a significant issue for utility solar photovoltaics and only includes temporary noise pollution due to construction. The last variable chosen was public health and safety. Health and safety concerns of onshore wind and utility-scale solar photovoltaics include increased levels of dust, increased local traffic, increased demand on local temporary accommodations, temporary disruption of outdoor recreation activities, and loss of traditional areas, which are all concerns for oil and gas as well. These all can be mitigated through various measures such as application of dust suppressants, creating a traffic management plan, hiring local and public and indigenous informing and consulting. Another concern with solar photovoltaic is solar glare, which is reflected light from solar panels into the surrounding project areas, and can be mitigated with solar glare hazard studies to ensure there is no glare for nearby facilities, major roadways, or flight paths. The main public health and safety concern with oil and gas is air pollution. Drilling and combustion has led to increased concentrations in nitrous oxides, particulate matter, and ozone. Exposure to these pollutants can lead to adverse health outcomes such as respiratory problems, cardiovascular disease, and cancer. Studies have shown that residents living half a mile from unconventional gas well sites were at greater risk of air pollution health effects than those living further away. We will now analyze and discuss the results of our data collection, as well as potential limitations. The variables chosen for the cost-benefit analysis can be divided into the three pillars of sustainability: economic, environmental, and social. First is the economic pillar, which includes the levelized cost of electricity, payback period, energy return on investment, energy payback, employment opportunities, and efficiency. Overall, wind and solar energy are on par, if not more economically sustainable than using oil and gas for energy generation, with wind energy currently being slightly more economically sustainable than solar energy. Drawbacks such as lower efficiencies and intermittent energy generation have solutions such as new technologies and energy storage currently being researched and developed, making renewable energy an even more economically viable option in future years. The variables related to the environmental pillar include emissions, land use, and biophysical environmental impacts. Overall, renewable energy systems are more environmentally sustainable in comparison to oil and gas due to lower emissions and decreased impact on the biophysical environment. The large land use requirement of renewables is mitigated through dual land use and is currently being researched for more land-efficient designs. For the social pillar of sustainability, the related variables are noise pollution and public health and safety. Overall, from the variables analyzed, it is clear that renewables are a significantly more socially sustainable energy source compared to fossil fuels, as they have notably less noise and air pollution. There were various limitations with our study. Not all data found in the data collection was Alberta-specific or from recent years due to the data not being easily accessible or publicly available. Our methodology could be improved by assigning weights to each variable and ranking the energy sources for a definitive answer to our research question. However, this was not feasible due to the time required for this type of analysis and due to our individual biases, potentially skewing the weighing. We will now discuss our conclusions and recommendations for the study. The purpose of our project was to determine the best renewable energy option for Alberta and to determine what energy source could potentially replace or supplement the oil and gas industry. We conducted this project through a holistic cost-benefit analysis with variables chosen aligning with different aspects of the sustainability pillars. The scope of our project included onshore wind, solar photovoltaic, oil, and natural gas as energy sources. Our variables chosen are listed below. From our analysis, we determined that wind and solar are on par with oil and gas for economic sustainability, and more environmentally and socially sustainable compared to oil and gas. With solar and wind energy both being intermittent sources, and Alberta having significant resources of both, it would be impractical to choose one over the other. Despite the benefits of renewable energy in regards to sustainable development, there are still many hurdles that must be overcome, such as public approval, market integration, and changing regulatory frameworks. However, the role of renewable energy in Alberta's path to a sustainable future and a net zero 2050 is critical and can only be realized through supportive policy frameworks, technological innovations, and active collaboration among stakeholders to overcome existing barriers and fully harness the province's diverse renewable resources. Thank you for listening to our presentation. Here are our references.